Welcome back, everyone. So today, we're taking a pretty fascinating journey together. We are quite literally going to build the universe from scratch. Well, geometrically speaking, at least. No hard hats required for this one. If you've ever looked at a skyscraper, a suspension bridge, or, honestly, even the screen you're staring at right now, and wondered about the hidden structural logic holding it all together, you are absolutely in the right place. We're going to go step by step through the fundamental building blocks of space in this explainer. We'll start from absolutely nothing and build all the way up to advanced logical reasoning. And hey, don't let the word advanced scare you off. I promise, by the time we wrap up, you are going to see the world in a completely different, highly structured way.
I absolutely love this quote straight from our source material today. It's geometry for the regular kid. And you know what? That's exactly our mission here. Whether you're a student trying to brush up on some math skills or just a curious mind wanting to understand the mechanics of shapes in space, this incredibly complex subject is 100% accessible to you. We're stripping away the confusing jargon and we're just going to focus on clear, logical steps. Truly, if you can visualize a simple dot on a piece of paper, you already have exactly what it takes to master everything we're about to cover.
Okay, here's our roadmap. First, we'll welcome you to the geometry zone. Next, we'll cover points, lines, and dimensions. Then, entering the flat plane. After that, we'll look at when shapes and lines intersect. And finally, we'll unlock the power of geometric proofs.
Welcome to the Geometry Zone, the study of shapes and space. Let's dive right in.
Section 2. Points, lines, and dimensions. We are starting from zero. Before you can have a shape, before you can even have a basic line, what do you actually need? You need a starting point, literally. And that brings us to our absolute first building block, the point. Now in geometry, a point simply indicates a location. But here's where it gets kind of mind-bending. A point actually has zero size, none. It has no width, no depth, and no length. It is a literal zero-dimensional concept. It just marks a highly precise spot in space. When we draw a little dot on a page to represent a point, well, that's just a physical representation so our human eyes can make sense of it. But in true geometric theory, it takes up strictly zero space. It's pure location.
Okay, now picture taking that single zero-dimensional point and just stretching it out forever in two completely opposite directions. Boom, we've just birthed the first dimension. A line is a straight path that extends infinitely. It finally has length, sure, but it still has absolutely no width or thickness. It is completely flat. Usually, to name a line, we'll just pick any 2 points that sit on it, and we assign a little double-sided arrow above those letters just to remind ourselves that it never ever stops going in both directions.
So as we start dropping more points into this new one-dimensional space, we need a way to talk about how they relate to each other. If you have a bunch of points that all share the exact same straight path, we call them collinear points. Think of them as roommates living on the exact same infinite line. But if you have points that are not on the same straight line, like say they veer off somewhere else entirely, those are non-collinear. And this distinction, it's absolutely crucial because when points don't perfectly line up, they create the opportunity to form angles, corners, and eventually the 2D shapes we all recognize.
And this brilliantly illustrates what happens when those 1D lines start interacting in space. We suddenly get these very strict relationships. For instance, when 3 non-collinear lines connect at 3 vertices, they form a triangle. Or, if you have 2 lines that run perfectly alongside each other and never ever meet, no matter how far into infinity they go, those are parallel lines. And if 2 lines cross each other so perfectly that they form 4 exact 90-degree right angles, those are perpendicular lines. It's amazing, right? We're already building a complex, structured world just from zero-dimensional dots and infinite straight paths. Section 3. Entering the flat plane. Expanding into 2D. We need a place for our flat shapes to actually live.
We have officially entered the second dimension, the plane. A plane is a perfectly flat surface that extends infinitely in all directions. Think of it this way. If a line is a never-ending tightrope, a plane is a never-ending sheet of perfectly smooth ice. This is the flat geometric space where all our 2D shapes exist. So anytime you draw a square or a circle on a piece of paper, you're basically representing a 2-dimensional shape on a physical plane.
Moving to Section 4, when shapes and lines intersect. Here is where we start smashing dimensions together.
Now, what's really interesting about this is visualizing the strict rules of how space interacts. When 2 simple lines intersect or cross each other, they meet at exactly one single, zero-dimensional point. Makes sense, right? But what happens when 2 infinite flat planes intersect? They don't just meet at a tiny point, they actually meet along an entire one-dimensional line. And get this, If you pierce a flat plane with a single line, kind of like sticking a sharp pencil straight through a sheet of paper, their intersection is once again a single point. You can see this logic applied perfectly on 3D objects, where the flat planes of the sides meet at distinct one-dimensional lines, which we call edges.
Finally, Section 5. The power of geometric proofs. These are the rules of the game.
Up to now, we've built our universe visually. But in mathematics, just trusting your eyes simply isn't enough. We have to move from visualizing into pure, unbreakable logic. Which brings up the ultimate question. How do we mathematically prove what our eyes are seeing? If two lines look parallel, how do we know for sure? If an angle looks like 90 degrees, how do we prove it beyond a shadow of a doubt? Well, we do this by communicating mathematical ideas through proofs.
To actually build a proof, you've got to understand the difference between your two main logical tools, postulates and theorems. Think of a postulate as our baseline. It's a statement so fundamentally obvious we just accept it as true without needing a proof. For example, through any 2 points there is exactly one straight line. That's a postulate. We just accept it. A theorem, on the other hand, is a statement that has to be proven true by meticulously stacking up definitions, postulates, and other proven theorems to back it up. The absolute most common way you'll do this is the two-column proof. And listen, don't let proofs intimidate you. They're essentially just really structured logic puzzles. Here are the core steps to beat the game. First, make a game plan. Draw out a picture, label what you know. Second, always start with your given information. Those are the freebie facts the problem literally hands to you. And third, and this is the golden rule of geometry, folks, give every single statement a reason. You literally cannot make a leap of logic without backing it up with a postulate, a theorem, or a formal definition.
Let's move to and see how this builds in action. The setup is simple. You have your statements, the math claims you are making, paired right alongside your reasons, which is your legal, logical justification for making that claim. Notice how we start with the given facts right out of the gate. Say we know a line segment is geometrically congruent to another. Our next logical step is to say, well, if they are congruent, their lengths must be equal. And the reason for that leap? Simple, the definition of congruence. From there, you might substitute the actual algebraic equations in and ultimately use something like the division property of equality to solve for your variable. The beauty is that every single logical step you take is perfectly mirrored by an unbreakable reason. That is how you build a rock-solid proof. So, what is the crucial takeaway from all of this? It's that geometry is definitely not just a set of abstract shapes in some textbook. It is a rigorous step-by-step system for understanding the architecture of our entire physical reality. Think about it. We went from a zero-dimensional point, stretched it into a line, expanded it into a flat plane, smashed those planes together to find intersections, and finally learned how to logically prove it all. So, I'm going to leave you with this challenge. Take a second right now and look around the room you are sitting in. Look at the corners of your walls, the flat plane of your ceiling, the straight edge of your desk. Where are the intersecting planes? Where are the collinear points? Use this new toolkit to analyze